Shock waves cause a vast increase in drag and may cause serious control troubles. One way of avoiding these troubles is to put them off to still higher speeds by raising the aircraft's critical Mach number. There are two chief design methods for doing this. The first is to use relatively thin wings. That is, wing sections with maximum thickness small compared with width or chord. Thin wings in this sense can, of course, be very deep. The thinner the wing, the less the air is speeded up, and so the critical Mach number is raised. These two wings are of the same general shape and at the same angle of incidence. The tunnel speed is the same for each. As it increases, the shock wave forms on the thicker wing at a Mach number of 0.8, but not a sign yet on the thinner one. Here it comes at last, at a Mach number of 0.9. But wings can't be made too thin, or the landing speed would be too high. The other important way of raising the critical Mach number is by the use of sweepback. To understand this, let's look from above at the flow over a wing. The contour of the wing section determines the amount the air is speeded up. Now sweep the wing back. We can represent the velocity of the airflow ahead of the wing by an arrow of a certain length. We can consider this velocity as made up of two smaller components. A yellow component at right angles to the leading edge, and a red component parallel to the leading edge. The red component can be considered to flow along the span and is not speeded up by the wing section. But the yellow component flows across the section and is speeded up by it. It is therefore only this component which affects the wing's critical Mach number. So the maximum speed reached over the swept wing will be less than it would be over a similar straight wing. In particular, if the flow over the straight wing has reached the speed of sound, at the same flight speed, the flow over the swept wing will still be subsonic. The swept wing has, therefore, a higher M crit. The greater the sweep back, the more the critical Mach number is raised. For instance, suppose the straight wing has a critical Mach number of 0.8. By sweeping the wing back to 35 degrees, the M crit is raised to 0.98. But this is only the theoretical result for an infinitely long wing. In practice, the critical Mach number would only be raised to about 0.9. Sweepback, like thin wings, brings its own problems at low speeds, such as tip stalling. So designers must compromise between high speed and low speed requirements. And aircraft designed to fly near the speed of sound use thin wings together with sweepback to obtain a high critical Mach number. Various arrangements have been adopted, all very different in appearance. If the swept wing is too thin to contain the engines, they can be mounted externally in pods. Alternatively, the engines can be buried in the wing roots, which are more highly swept than the remainder of the wing. A special kind of sweepback is the crescent wing. Here, the sweepback is reduced in stages to avoid tip stalling. The delta wing combines a high degree of sweepback and great strength. The Delta's large wing area makes it very maneuverable and gives it a good performance at high altitudes. The simple Delta shape can have many variations. Some Deltas have a tailplane to improve maneuverability at the expense of slight extra drag.